You're listening to the Futures Podcast with me, Luke Robert Mason. On this episode, I speak to neuroscientist David Eagleman.
You can actually plug in completely new kinds of data streams, and the brain will say, oh, I get it. It's correlated with reward or with this, and it figures out how to use it.
David shared his insights into the mystery of neuroplasticity, how modern technology impacts our brain's development, and the different ways we might soon be able to augment our senses and enhance our cognition. This episode is an edited version of a recent live stream event. You can view the full unedited video of this conversation at futurespodcast.net. Exciting new discoveries have revealed that the brain is a dynamic system constantly modifying its own circuitry. In his beautiful new book, Live Wired, neuroscientist David Eagleman looks at how this unique property, known as neuroplasticity, enables us to gain the skills, faculties, and practices that make us who we are. But more important than that, he shows that by testing the limits of this odd quirk, we might be able to develop a profoundly new relationship with technology, one that might eventually enable us to augment our senses and choose how to experience our reality. So, David, it seems to me that when we talk about the brain, we use so many computational metaphors. We compare the organ itself to a computer and then claim that the mind is like software running on a machine. But this book attempts to get away from these limited metaphors, and you've done that by coining a brand new term, and that term is live wired. So what does it mean to have a brain that's live wired, and what are some of the key features of this live wiring?
Yeah, so first of all, Luke, it's great to see you again. Great to be back here. And the key in answer to that question is, so I live in Silicon Valley. All the talk is on hardware and software, and engineers are praised for making very efficient and trim versions of this. But in fact, what's going on under the hood is so different than that. What you have is this 3 pounds of remarkable machinery that is constantly reconfiguring itself every moment of your life. So you have 86 billion neurons, each of which has about 10,000 connections. So you have like 0.2 quadrillion connections in the brain. And these are constantly seeking and finding and plugging and then unplugging and replugging and so on. Everything that you learn, everything that you do causes physical change in the structure of your brain. So, Luke, we've known each other for some years. And, when I first learn your face and your name, there's a physical change in the structure of my brain. And that's what allows me to remember that. But over the course of years, all these massive changes orchestrated across the gargantuan fabric of your brain adds up to what we call you. And this is a completely different sort of thing than hardware and software, because it's not about efficiency. Instead, it's about taking things that you're doing that are relevant to you, that are rewarding or punishing, and burning this down into the circuitry at different levels, all the way to the DNA, changing the way that the DNA is expressed as a reflection of your experiences. And so the term of art in our field is brain plasticity. But the reason I kind of want to get over that term is because that was coined 100 years ago to represent the way that you can mold, for example, a plastic toy and it holds on to that shape. That's what a plastic thing means, is that you can mold it and it holds it. But although people were impressed by that 100 years ago, that's not what the brain is up to. It is constantly changing, as I said, every moment of your life. And so I needed a new term for that. And so liveware is the term that I use nowadays.
Well, what does this process teach us about the profound relationship that we as human beings have with both our environment that we inhabit and the society that we live in?
Yeah, well, it turns out I'm old enough to remember in the year 2000 when the Human Genome Project got completed. We were all so excited about this because we thought, wow, once we have all the letters of the DNA, we're going to understand so much. But it turns out that doesn't tell us much at all. And it's not that the project was a failure, but it's just, it only tells us half of what we need to know, because the other half of what makes your brain and my brain is all around us. It's every experience we've ever had. It's the language we're exposed to, the culture, the beliefs, the parents, the friends. Everything in our lives is what determines how our brains wire up from there. DNA is just the first domino that gets kicked over. From there, people go off on very different trajectories. I actually start the book Live Wired with a quotation from Martin Heidegger that I love. And the quotation is, every man is born as many men and dies as a single one. And what he's getting at there is we start with so much potential of what could happen to us. But of course, life happens and it molds us into a particular shape. And by the time we're on our deathbed, you are exactly you. So you are your experiences in the world. In fact, the way I'm thinking about it a lot lately is that each of us is a little vessel of space and time, as in where you grew up in your year that you were born and so on, and where I grew up in exactly when I was born, the experiences that I had. I'm a vessel of all those, and you're a vessel of yours. And as a result, by the way, everyone's quite different from one another. We all like to think when we're kids that everyone is the same on the inside. But in fact, because of our experiences, people can end up being quite different from one another. But we have this very low bandwidth communication channel of language with which we can communicate from, my planet to your planet. But yeah, it's because our experiences are so vastly different from one another.
It reminds me of the children's poem, I am the only me I am who qualifies as me. No me I am has been before and none shall ever be. But when we hear this idea that our brain is neuroplastic, or that our brain changes, that feels really odd, because we've all seen photographs of the brain and it's this 3 pounds of grey gloop and it looks very fixed. So how exactly do these changes in the brain actually occur, and what motivates these sorts of changes?
Yeah, I mean, it's an excellent point that you raise, and that I think is why for the last hundreds of years we've just assumed the brain is fixed. And when you look at any neuroscience textbook, what you find is, okay, here's a picture of the brain. This is the part for seeing, there's a part for hearing, for touch, for smell, for taste, and so on. And in fact, I feel like it's such a wrong-headed start to even think about the brain, because it's an extremely fluid system. An analogy that I make in the book actually is, it would be as though, for example, when a child looks at the globe and all those country lines in there, they assume that those are somehow fixed and they had to be that way. But we know as you get older that if history had changed even just a little bit, this king had died young, or this battle had tipped the other way, or whatever, the country lines would be different. It's a very fluid sort of thing. Anyway, what happens in the brain, for example, is if somebody goes blind, the visual cortex, the part at the back of the brain that we label in the textbooks as here's the visual cortex, that gets taken over. That becomes used for touch, for hearing, for memorization of vocabulary words, for other things. And it's not the visual cortex at all. And the way to think about this is that colonization is a full-time business. So an analogy that I give in the book is just what happened with the Americas when the French and British and Spanish were all competing for the territory. And, in 1750, the French had a huge area here. The French had like the whole major swath of the Americas down the middle. But what happened is they just weren't sending enough ships over compared to the British and the Spanish. And so eventually they lost their territory. And the reason I use that analogy is because this is the key about how the brain makes a map of the body and understands the body, is it depends how many ships of data are coming in. So for example, if you lose an arm, there's no more ships coming from the arm. And so your brain's map changes. It says, oh, okay, I got it. I'm a body without an arm. That's cool. It changes. If you go blind, the visual cortex gets taken over. If you go deaf, the auditory cortex gets taken over, and so on. The key is that nothing lies fallow in the brain. There's competition for territory. It'd be like if a restaurant in London went out of business, it's going to get taken over by some other business because none of the real estate's going to get unused.
It seems like this process is so delicate in many ways. I mean, is brain plasticity one of those things that is highly active when we're very, very young? Is it really important how we grow as children, especially in those first 10 years of our life? And if it is, how should we encourage more playful interactions with the world that have positive outcomes for our neuroplasticity?
Yeah. So what you're pointing out is something very important, which is, what Mother Nature has done with Homo sapiens in particular has been a particular trick that she's tried, which is drop our brains into the world essentially half-baked, as opposed to many other, like let's say an alligator, when it drops in the world, pretty much knows what's up. It knows, okay, I've got programs for eat, swim, mate, so on. A zebra, when a zebra is born, it runs in 45 minutes. A dolphin is born swimming and so on. But human infants have these super long infancies and helplessness period. And it takes a long time to learn how to walk and a long time before it reaches adolescence and so on. And it's because we don't come pre-programmed. We come ready to absorb the world around us and all of our culture and language and beliefs and so on. And so that's a really great strategy on Mother Nature's part, but it is also a gamble because what it depends on is getting the right sorts of inputs. And most of us do get that. Most of us are lucky enough to get that from our parents, love and language and attention and touch and things like that. But there are these tragic natural cases where children don't get that. One case that I covered in my television show, The Brain, is the issue of the Romanian orphanages. After the fall of Ceausescu, there were tens of thousands of kids in these orphanages because their parents had been killed, and it was too much for the staff. And so they said, look, just don't talk to the kids and don't pick them up because otherwise the kids will get clingy. And so these kids grew up without the proper input, and as a result, they had major cognitive deficits as a result. And we see this in really tragic cases when a child is so severely neglected that they don't have an adult talking to them or giving them love. They end up with really deep problems, like they don't even learn language. They can't even learn how to chew solid food or see across a room or things like this. And the problem, as you pointed to, is the door closes at some point. You only have a certain number of years to get that input and develop the brain. And after that, it is too late. And so, yes, it is a lesson for all parents to make certain that you're giving your child plenty of love and attention and touch and language and so on.
It seems, you talk about those tragic moments, it seems as if sometimes those tragic moments are the things that can teach us the most about the human brain. I mean, with things like neuroplasticity, surely neurological disease and damage to the brain, those things can teach us so much about our ability and our resilience of our brain. So I guess, David, my question is, do neuroscientists sit around all day and wait for motorcycle accidents where they can get split brain syndromes? Or is there other ways to observe this property in the brain as a scientist?
Yeah, I mean, so I'll tell you how I do it. So by the way, as far as waiting for clinical cases, tragically there are plenty of clinical cases that come in every week, and so it's easy enough to see evidence of these things and understand what's going on that way. And then of course there's animal research where people do things like implant an infrared detector directly into the cortex of a rat, and you see whether the rat can come to understand infrared light. And by the way, it can come to understand and then do tasks based on seeing infrared. Why? Because the cortex, the wrinkly part on the outside, it's a one-trick pony. The whole key with the brain, and this is really the framework that I lay out in the book, the whole framework is that you can feed any kind of data into the brain and the brain will just figure out how to use it, because the brain is locked in silence and darkness. All it ever sees are spikes. It doesn't know whether those spikes represent photons from the eyes or air compression waves from the ears or mixtures of molecules from the nose or pressure on the fingertip. It doesn't know. All it knows is, there's spikes coming in, and it's good at putting together a story of how to correlate these things. Like, I've noticed that whenever this comes in, this is coming in. And so the point is, you can actually plug in completely new kinds of data streams, and the brain will say, oh, I get it. It's correlated with reward or with this, and it figures out how to use it. And so one of the things I've done is I ended up spinning a company off of my lab where we build devices. So for those of you on the video, on the YouTube can see this, I'm wearing a wristband, and this is a wristband that has vibratory motors in it. So it's got these little buzzers like the buzzers in your cell phone. This is called the Neosensory Buzz. And what it does is converts any kind of data stream into patterns of vibration on the skin. And so, for example, one of our main areas is with people who have hearing loss. And so we capture sound, turn sound into patterns on the skin, and people who are completely deaf can learn how to hear through the skin of their wrist. And it's because that data climbs up the spinal cord into the brain, and the brain says, oh, I get it. I'm seeing the dog's mouth move, and I'm feeling the buzzing on my wrist, and I understand that those are correlated. And then, I clap, I ring my doorbell, I do these things, and I see that these sounds are correlated with what's happening on my wrist, and they come to hear that way. And by the way, we don't remember, nobody remembers, but when you were an infant, you had to learn how to use your ears. Ears don't come pre-programmed to work. You're getting all these spikes coming into your brain, but you see your mother's mouth moving, or you bang on the bars of the crib, or you clap your hands or whatever, and your brain starts putting together these correlations, and eventually you hear.
Well, let's talk. I want to talk so much about neosensory, but before we do that, let's just establish this idea around the senses, because it feels like the heart of this is how we interact with our sense organs. And correct me if I'm wrong, but it feels like we receive signals via our sense organs. Our brain then processes these signals, and we almost project the world back out there. And in doing that, we often obscure many aspects of objective reality. You talk about in the book how we don't see the blood vessels in our eyes, for example. So what exactly is going on here with this feedback loop between the sense organs, the signals it receives, and the brain?
Great question. It turns out the brain's job is to build an internal model of the world that's out there. It's just in this little 3-pound control room that it's in, and it's controlling this huge empire of the body, and it's moving through the world and getting this electromagnetic radiation and air compression waves and so on. And it's trying to understand what's going on out there. And so what you see isn't actually reality, of course. I mean, just as an example, colors don't exist. It's just different wavelengths of electromagnetic radiation, but your brain puts together this thing. Why? Because it's a fast way of tagging something. So it says, oh, there's ripe fruit in the trees, the red against the green there. Great. It's just a way of, instead of saying, okay, let's see, that's 462 nanometer wavelength and that's 570, it says, okay, great. I'm just going to call that red and green and have a direct perceptual experience. But, one thing that's really interesting to me is, for example, visual illusions, which is something that's interesting to little kids and then to neuroscientists when they grow up, because what it demonstrates is this issue about, wow, what's actually out there has nothing to do with what I believe I am seeing. And this is because what you're seeing is just an internal representation. I'll give you an example, which is, take vision. Vision has very little to do with the eyes. And you can have rich, full visual experience with your eyes shut. And this is what we do every night when we dream. And this is because vision is all about the internal activity going on in the brain. And your eyes, just from the point of view of the number of fibers that it sends to the visual cortex only gets 5% of its input from the eyes. All the rest is, feedback loops and, other parts of the brain. And so you're not exactly seeing the world out there. It's just that you have the capacity to, if you're confused about something, you can really stare at it and try to incorporate more data. But mostly all you're ever seeing is your internal model of what you believe is out there. And this is why magicians and illusionists and so on can do what they do, because that's all you're seeing, and you believe you have seen something.
Well, that's such a wild and crazy idea. And you talk about dreaming actually a lot in the book, and you have a theory for why dreaming exists, and it's very heavily tied to brain plasticity. It's because our brain has this property that we need to dream, otherwise, basically, it sounds like we'd go crazy. Is that right?
Well, so here's the whole key. So one of the big discoveries in neuroscience, so I mentioned, for example, if you go blind, your visual cortex gets taken over. It's no longer visual, right? But one of the big discoveries, to my mind, was how fast this happened. So it turns out if you take sighted people and you blindfold them and you stick them in a brain scanner, within about an hour, you can start seeing little blips of activity in the visual cortex from things like sound and touch. So in other words, this encroachment of one territory onto another starts happening very rapidly. And so that was the big surprise to me, is how fast the system is wired up for this. So with a student of mine, we started this project years ago. We realized that there's a problem that the visual system has that the other senses don't, which is that the planet rotates into darkness for half the time. And in the dark, you can still hear and smell and touch and taste just fine, but you can't see. And of course, I'm talking about evolutionary time, not recent electricity times. And so the theory that we ended up deriving was that dreams are the brain's way of defending the visual cortex at nighttime against takeover from sound and touch and other areas. And so it turns out that we've now done deep studies on this. For example, the paper we just published is on 25 different species of primates. We look at how plastic the primates are. And some, like lemurs, are not particularly plastic. They drop out, they walk quickly, they reach adolescence quickly, and so on. Whereas Homo sapiens at the other end of the spectrum are very plastic. We have to absorb the whole world. And it turns out you can correlate the amount of REM sleep, rapid eye movement sleep, which is what correlates with dreams. You can correlate that exactly, which is to say, if you are a not very plastic animal, you don't have much dream sleep because you don't need it. You don't need to defend the visual cortex because it's not in danger of getting taken over because the system isn't moving around very much. In contrast, if you're a Homo sapien, the whole system is very fluid and flexible. And so you need to defend the visual cortex at nighttime against takeover by having dreams. And if you look up the circuitry that underlies dreaming, it is very specific. It's the circuitry that every 90 minutes comes on and just blasts the visual cortex with activity. And that's all it does, is just shoves activity in there. And of course, because that's the visual cortex, you see and you think, oh, I'm riding across the meadow and there are whatever, silver leprechauns or whatever your dreams. But that's how you keep it defended. Yeah.
So if you have very, very vivid dreams, does that mean your brain is very, very neuroplastic or brain plastic?
I think it's a separate issue about the vividness of your memory, whether you can remember. Yeah. Yeah. But one of the things we're looking at now, by the way, as a side note, is what happens when people don't have much in the way of dreaming. And it turns out that some people on tricyclic antidepressants or monoamine oxidase inhibitors have less dream sleep. And so we're just starting to study this about whether there are changes in the size and activity of their visual cortex, in the morning as a result of not having dream sleep.
Well, it feels like the brain is so fickle then that any small thing within the environment could have a massive change, and the environment then has this profound effect on our brains, which, as I was reading your book, it just reminded me of artist Douglas Copeland's famous quote where he lamented, "I miss my pre-internet brain." And I have to ask, what do you think the role of modern interconnectivity and modern technology and things like the internet have on the Western brain?
Yeah, I'll tell you, I am very cyber optimistic about this, and I'll tell you why. It's because what makes your brain what it is the diet of information that you're taking in. And when I grew up, I had my homeroom teacher, and when I really wanted to know something, my mother would drive me down to the library, and I'd pull out the Encyclopedia Britannica, and I'd look something up, an outdated article by 10 or 20 years, and hope to find what I needed that way. And of course, in school, I had lots of just in case information, like, just in case you ever need to know these 7 important dates in, Canadian history or something. And so totally boring. It's hard to make brain changes when you don't really care about the thing. In contrast, my kids, we have an Alexa and a Google Home, and of course they're on Wikipedia and whatever. Whenever they're curious about something, bang, there is the answer. And it turns out that when you are curious, you have the right cocktail of neurotransmitters present. And so it really sticks. And so this is just-in-time information versus just-in-case information. And it makes a big difference in terms of brain plasticity. And by the way, I run into like 13-year-old kids all the time who say something really smart. And I say, my gosh, how did you know that? And they say, I saw it in a TED Talk. And we didn't have that opportunity when I was growing up. I had my homeroom teacher. I didn't have the best person on the planet giving the best talk of their lives in 15 minutes, giving me a whole sense of what's going on here. But this is just standard mother's milk for these kids growing up now. This is why I think the next generation is going to be much smarter than we are, because they've had a much richer diet of intake, and they can actually surf into if you imagine all the world's information as a big sphere, they can enter any door they want to because they're interested in whatever bugs or baseball or ballet or whatever. They can enter that door, and then they start seeing other things. And that's interesting. They follow a path and so on. So I'm very optimistic about this. Let me just say one other thing, which is people, even neuroscientists, often have strong opinions about this, where they make some declarative statement about the effect of growing up digital. But from a scientific point of view, this is a very difficult thing to study because there's no appropriate control group. So if you take an 18-year-old kid who's grown up wired, you can't find kids who did not grow up with the internet as a comparison group. You can find kids, of course, who are totally impoverished and don't have the internet because they're in rural China or the favelas of South America or something. But there's 100 other differences there. Or you can find kids, you can compare them to 18-year-olds of the previous generation, but there's also 100 other differences there in terms of politics and economics and nutrition and pollution. There's just tons of other. So it's very difficult to do that comparison. So what I'm basing my answer on is just an understanding of how the brain works in terms of the diet of information it brings in, and it remixes things, and that's how it comes out with new ideas about stuff.
I mean, I'd love that you're a cyber optimist, David, but have you recently spent any time on Twitter? And in other words, what I mean is the media space that we're in, it already feels like it has this massive impact on our perception of reality. We live in these media silos, these reality bubbles. It must be having some form of effect on our brain, whether negative or positive.
I agree, although, as I said, we're just not going to really know what that effect is. But I will say this whole thing about bubbles, I'm not totally convinced that anybody's living in a bubble, because the reason people go on Twitter and Facebook and so on is because they want to get outraged by the fact that somebody's saying this or that. And so everybody reads the other comments on things. So it's not like we're in a silo or a bubble. In fact, what you're seeing is the, let's call them magnified or exaggerated opinions of the whole world around us. Yeah, so that's the thing. In a sense, we are exposed to more information than we used to be, and it might make everybody mad, and we might feel like, that person is crazy for believing X, Y, Z, but at least we're seeing it.
Unfortunately, sometimes we're seeing it. I mean, I was so happy to see this book come out. I mean, it was a book that you spent 10 years working on, and I've seen a multitude of your talks teasing this possibility of what I see as creating cyborgs using this unique ability of the human brain. And as I was reading your book, I kept thinking of Marshall McLuhan's famous quote where he said, "The extension of any one sense alters the way we think and act, the way we perceive the world. When these ratios change, then men change." And some of the best examples are captured in this book in the field of sensory substitution. So what is sensory substitution, and why is it such a good example of brain plasticity in action?
Yeah, it's this sensory substitution is feeding data to the brain via an unusual channel. So, for example, with the neosensory buzz, feeding sound information through the skin. One would think, well, that's crazy. That would never work, but it works just fine. And it turns out it's because the brain is just so good at taking in data and doing something with it. And people have been building devices like artificial retinas and artificial hearing, cochlear implants and retinal implants. And these things don't act exactly like your natural biological sense organs, but people figure out how to use them because their brains are plastic. And they say, oh, I get it. The data is now doing something a little bit differently. That's cool. I got it. So sensory substitution, one of the exciting areas is about for blindness, people feeding in data that way. So just as one example of many, some colleagues of mine have a device they've made called The Voice, which is VOICE, and the middle letters are capitalized, so it's OIC. But the idea is you're just taking, let's say, headphones in your phone, and you turn the video feed of the phone into sounds, and it scans across the scene from left to right. So it goes, and you're scanning what's going on, and what's happening is the brightness and the edges and so on all get turned into pitch and amplitude and so on. And at first it sounds like a cacophony and you bump into things. And after a little while, people get pretty good at understanding the visual world through their ears. Because as long as the brain gets the data, it figures out what it's going to do with it. So this is the idea with sensory substitution, and it works. And the reason I, am spending all this time launching a company out of my lab is because it's such a cool opportunity to take an idea in neuroscience and take it all the way from theory to practice. And now it's on, wrists all over the world.
I think we got to spend a little more time on this idea of sensory substitution, because the crazy thing about Peter Major's Voice, VOIC, is that people actually report seeing through the ears. And what they're describing is recognizing objects in three-dimensional space. In other words, what's experienced is actually a quasi-visual property. It's not an auditory property. It's visual, and that revelation is so important.
Yeah, I totally agree. I mean, the thing is, look at something like, it doesn't say something like reading a book. So, you're looking at these strange squiggles on a page, but because you are totally practiced at it, the meaning just flows off the page for you. You just say, oh yeah, this is the sentence, is what the meaning is. And it's only when you look at a foreign script, for example, if you don't speak Chinese or, the Northwestern Iranian language of Baluchi or whatever, like if you don't speak those, you look at it, you think, oh my God, how can anybody understand what these weird shapes and squiggles are? But it's the same thing with all of our senses. You're capturing photons or air compression waves, and you are having a direct perceptual experience. And it turns out you can get the data coming in through your ears, or there's another device called the BrainPort, which is a little electrotactile grid that sits on your tongue and translates a video feed into shocks on your tongue. And you can come to understand the world that way. People get pretty good with this thing. The idea of seeing through your tongue, it's so weird, but remember, the way we normally think about vision is just we've got these two spheres in our skull that are capturing photons and translating them into spikes. But we don't think twice about that. We think, oh yeah, of course, that's what eyes do. And of course I'm seeing. But you can get the information there via a different route.
But the key is it's not something you can just plug and play. It's more of a plug and wait sort of experience, a plug and pause sort of experience. These things take time to integrate themselves into the body schema. Is that right?
That's exactly right. You have to learn, you have to make those correlations. It's just like learning to ride a bicycle, for example. You can know everything about how it should go, but you need to go and practice it and figure out the relationship between input and output, as in, okay, I lean this way, oh, that happens. I turn that way, okay, that happens. It's the same thing with this. So just by way of example, with the Neosensory Buzz, the first day that people put it on, they see a dog's mouth moving and they feel buzzing on their wrist and they say, oh, I get it. That's the dog's bark. But it's still a cognitive translation. But after wearing it for a few weeks or a few months, they are hearing. It's not that they're cognitively translating. They say, oh, I heard a dog bark, and they look around for the dog. And that's because, it just takes time until the brain starts saying, before it starts having a direct perceptual translation of this. And this is what all of our senses are, but we don't stop to think about this normally. Vision and hearing and touch and taste and smell. It's just the brain's way of summarizing a whole bunch of data like, oh, you've got this mixture of molecules. I'm going to call that the smell of cinnamon. That's cool. That's what we're always experiencing. And as I said, it takes babies a while to learn what any of this means.
That's what this book seems to do such a good job of. It is that moment of, oh, I see. Oh, suddenly this thing that just seems so normal, almost invisible to me. Oh, goodness, there's all of these things that are going on in the background, all of these things that are being made invisible to allow me to have this perception.
Boy, that is right. And I actually think that is the main function of science communication, is trying to make those things that are normally invisible to us visible, where we realize, Jesus, what a weird situation we're living in here. And then, understanding what we can do with it and what we can build with that.
I have to ask, you've been wearing this Neosensory Buzz device. Do you mind me asking, how long have you been wearing it for now?
Oh, I've been wearing it for a long time, different prototypes of it along the way, where now this is the actual one on the market. But, it's interesting for a hearing person. There's an effect called blocking, which is to say your brain is trying to make changes so that it understands what's going on in the world. So my ears work fine. So when I get this data stream, it doesn't cause much change in my brain because it's redundant for me. But for a person who is deaf or hard of hearing, it makes big changes in their brains because that is the only way they're getting the auditory data. All that auditory data is a surprise for them. And so brains change predicated on surprise. So if you were going to ask, what's it like for me? For me, it's just a redundant thing where whenever I hear sounds, I'll tell you what one experience is for me wearing it. It's that we predict away things that we know are coming. So just as one example, everybody, when they put on, like my hearing friends, whenever they put on the Buzz, the first thing they say is, whoa, I'm hearing my own voice. Well, of course you're hearing your own voice. Your voice is probably the loudest thing you ever hear in your ear when you're in a conversation, but you don't feel normally like you're hearing your own voice. Why? Because it's totally predictable. You know what's going to hit your ear, so you totally ignore it. And it's the same, by the way, with things like toilet flushes and water in the sink and whatever. People say, well, my God, that's so loud. But normally we don't even pay attention to a toilet flush because we know it's coming, and so it doesn't seem that loud. But in fact, it is a quite loud event. When you are getting the data through a different channel, you recognize which things are loud that way.
So do you think you should ship the device with a pair of earplugs, perhaps, and maybe that's the way forward?
Yeah, I think so. For hearing people, yes. But so what we're doing with so people who are deaf or hard of hearing all over the planet now are using this and having really wonderful experiences with this in so many ways, from the simple things like, oh, I never knew that my microwave made noise or whatever the thing is, to really understanding like, oh, somebody is calling my name, or, this is whatever is happening here. Oh, I left this machine on and the machine's making noise. There's all sorts of ways in which this is helping people. But what we're doing with hearing people is we've built this to have an open API, and people can feed in any sort of data stream they want. And so we are experimenting with all kinds of new senses. So this is not sensory substitution, but now sensory expansion or addition. So by expansion, I mean something like, I hooked up a infrared version of this with one of the engineers from my company, where I can walk around and feel infrared light. And so the very first night that I was wearing it, I was walking in between two buildings, and suddenly I felt a bunch of infrared light. And I thought, where the heck is that coming from? So I followed my wrist, and it took me to an infrared camera that was surrounded by infrared LEDs. Normally totally invisible to us, but it's shining this big blast of infrared, it's a night vision thing. But it was totally obvious to me. Like, I just immediately saw through the camouflage just because I was wearing this. I had another sense. So I'm expanding the visual sense that I already have. Sensory addition is plugging in a completely new sense. So for example, I think I mentioned this, but like drone pilots, we can feed in the pitch, yaw, roll, orientation, and heading of a drone. So as they're flying, it's like they've stretched their skin up there. They're one with the drone. They're feeling the data directly from the drone. And that allows them to be able to fly in the fog or the dark because they know what the drone is feeling. And so that's an example of sensory expansion, because now it's something that's not even part of you, or it's not an extension of a sense you already have. And there are many, many examples like this. As you know from the book, there are tons of examples of this, ways that we can expand our sensory capacities.
Well, I want to get on to sensory expansion in a second, but before we do, there's another thing that this wonderful, weird brain plasticity allows us to do. In addition to adding new senses, it also allows us to leverage brain plasticity to interface with entirely new limbs or control alternative anatomies. So I guess my question is, might it soon be possible to control a robot with our thoughts?
Yeah, absolutely. This is one of the chapters that I wrote because from the time I was a kid, I would look at things like, just as an example, you look at x-rays of different animals and you see that, rats and bats and dogs and camels and elephants and whatever, they all essentially have the same architecture that we do, but they have longer this and shorter that and bigger this. And it's just like tweaks on the same basic plan. And what we've learned from genetics over the last 20 years is this has to do with not a completely different sort of, genetic plan. Instead, it's simply you turn on this gene for a little bit longer and you turn on this one for a little bit shorter time during the developmental program. And that gives you long legs or big long arms for wings like a bat, or this, or you just are tweaking very subtly these genetic knobs, and they get very different body plans. So the thing I started wondering about is, but I don't get it. How does the brain have to figure out how to operate a different body plan? Like genetically, do you have to pre-program it? And so what I realized is it is not that at all. Brains just figure out whatever body they happen to be trapped in. So as one example I use in the book, because it's just a lovely example, it's very visual, this dog named Faith that was born without front legs. And so Faith needed to, get to food and water and her mother and so on. So she learned how to walk on her back legs bipedally like a human. And so Faith walks around on her back legs. And it's not that any dog couldn't do this. It's simply that they don't need to. They don't bother. But the point is, it is not that her brain is pre-programmed to drive a dog body. Her brain is pre-programmed to seek, relevance and get information and get out there and do what it needs to do. And so it just figures out how to operate given the limbs that it has available to it. So can we drive robots? We already know the answer is yes. For example, there are people who are paralyzed who can drive robotic arms, just, using thoughts in their motor cortex, as in, okay, move my real arm. But of course, their real arm isn't getting the signals, so it drives this robotic arm. But we now know also it's easy to add, for example, a new limb, what's called supernumerary limbs. So just as one example, in VR, you can do these things where, let's say I'm holding two controllers and and in this game I can control my two virtual arms, but there's a third arm coming out of my chest in this virtual reality game, and I control that by tilting the controllers in a particular way, and that allows me to do that. And I'm supposed to grab boxes, and in about 3 minutes, people can figure out how to use a third arm pretty well. And so what this tells us is it just doesn't matter what body you find yourself in. People get into cranes and mech suits and so on, and it just doesn't take that long to figure out, oh, I see. I tilt to the left, I move this, and that moves that. Great, done. And so it's extremely flexible. And so one of the things that I suggest is that as we get better and better at using these telelimbs, we'll be able to, control a robot entirely, not even connected to it, just wirelessly.
I keep arguing this with anyone I get on the podcast who wants to talk about space. I keep arguing that maybe we don't have to actually send human beings to the moon or to other planets. What we can do is send a robot ahead of us, a bipedal robot, and then just embody that robot through this use of the thing like telelimbs. And we'd basically, if the brain is as plastic as you say, we would basically get the same sort of feeling as being on the moon, but here on planet Earth.
Yeah, I think that is probably our only option for long distance space exploration, because our bodies have evolved in this very particular oxygen rich environment, and we stink at actually going out to outer space to distant reaches. The only downside is, of course, the delay. It takes, X number of minutes to get a signal there and get a signal back. And so it wouldn't be exactly like you're running around the surface of Mars. Instead, it'd be a very slow process.
Or we could become another body entirely. And you talk about in the book, Jaron Lanier's term, homuncular flexibility, which sounds so odd and weird and wonderful. But that's because it is so odd and weird and wonderful, because what he's talking about is embodying these new weird morphologies, using virtual avatars to extend ourselves beyond the boundary of our skin and developing these profoundly new weird morphologies of tentacle beings floating in cyberspace. I mean, there's so much possibility here, isn't there?
That's exactly right. And it's all comes down to this very basic thing that the brain is trapped inside the skull. It doesn't know what your body looks like. It just figures it out. It just figures out what it needs to do. And this is why we can jump on pogo sticks and onto hang gliders and onto any weird device. You just figure it out. You say, oh, okay, I got it. That's how this works. And then you're off to the races.
I mean, the word that you avoid using in the book is cyborg. You mentioned one or two examples of individuals who aren't cyborgs, but hearing about all these developments and hearing about all the things that our brain can do, it just conjures for me this concept of the cyborg. It feels to me like neuroplasticity might actually be the key to interfacing, I guess, with advanced technology. But when I use the word cyborg, I don't mean Terminator, but what I mean is profoundly embodied cyborgs, people like Neil Harbisson, for example.
Yeah, I mean, that's exactly right. But it depends what you mean by advanced technology, because the advanced technology is the 3 pounds of wetware in the skull. That's the advanced one. The other stuff we have is just clunky metal limbs and stuff. But yes, we can marry those two technologies together. And that almost certainly is our future. I mean, the world 100 years from now is going to be very different. And one of the reason I wrote this book is because I feel like we are now on the cusp of a massive revolution that can happen in terms of our engineering, in terms of the way we build things. And so, as I said, I've spun a company off my lab to do the sensory bit. As far as the motor output bit, there's so much opportunity there. And I feel like with Darwin and his theory of evolution, the idea was, hey, wow, DNA is really important. And that was a massive step. But now we know that DNA is only half the story, and the other half of the story is everything that happens to you, everything around you that you absorb from the world. And so that feels like that's the next step of where we're going now. One of the things that I write about in the book that feels very important to me is when we sent the Mars rover Spirit up to Mars. It's a multi-billion-dollar project. It landed on the surface of Mars, rolled around for a while, did a great job, and then it got its right front wheel stuck in the soil and it died. And if you compare that to, let's say, a wolf will get its leg caught in a trap and it will chew its leg off, and then its brain figures out, okay, how do I operate a body with only 3 limbs? Okay, cool, got it. And wouldn't it be great if we could be building robots that say, oh, my right front wheel is stuck in the Martian soil. I'm going to chew my wheel off, and then I'm going to figure out how to operate this, not in the way that was pre-programmed, but I'm just going to figure this out because I need to get somewhere. That's the kind of machinery that we will be building next.
Well, but that's what makes artists like Neil Hobison, the colorblind artist who has an antenna that allows him to hear color. That's what makes him so interesting, because he's not thinking about the cyborg as something whereby we have to just cram data and ones and zeros into the brain and avoid the bottleneck of the senses. He's actually embracing the senses, or the sense organs, and creating new sense organs and developing devices which eventually he sees as an organ. You go up to Neil and you try and touch his camera and he recoils as if I came up to you, David, and tried to touch your nose. I mean, these individuals doing these sorts of experiments become very profoundly embodied with the devices that they're wearing and the new organs that they're creating. And part of that comes from just duration, being with it and allowing the brain to eventually adopt it. In Neil's case, he now dreams these crazy sonochromatic dreams when he's not even wearing the device. So it just feels like this is the place we should be starting at.
Oh, that's exactly right. That's exactly what Neosensory is doing for that reason. And by the way, I think, the reason you would recoil with your eyes, your nose, or your ears or something if I tried to touch it would be for exactly the same reason as you're saying, which is that. But the thing I want to point out is that these are random, weird devices that Mother Nature has cooked up, but we have incorporated them into our sense of self. And I have a section in the book, as you know, where I'm talking about what does it mean for something to be part of the self? It's something that you're getting data from or that you can control with your motor output. And anything that fits that becomes incorporated into your sense of, okay, that's part of me. And so therefore, I think when we launch robots into outer space and so on, it will really feel like me. And so the robot you're controlling that's on the moon, if someone comes up and kicks it or threatens it, you're going to feel that in a bodily way. You're going to recoil at that.
You're developing a company from this wonderful little quirk that we have about the human brain, but so many people could start developing their own devices if it's just purely about creating something that translates available data into some sort of waveform, analog information through a software process that then the body can understand. Then potentially anyone could design a bespoke sensoria. We could create bespoke synesthesia to start designing our own sensoriums. Surely that's a wonderful egalitarian view of how we might all individually navigate the world.
Absolutely. And there are biohackers all around us who are doing cool things. Like just, one example that you know about is implanting magnets into your fingertips. And then people who do this can feel, for example, the electromagnetic bubble around, a plug and adapter. And, I know one guy who does debugging this way of computer systems. You feel, oh wait, this part's off, but it's supposed to be on. But you can feel where there's electricity running through an electromagnetic bubble. And so, yeah, exactly right. I think people will increasingly be doing this. And again, the reason I feel like we're on the cusp of an important moment in history is exactly because we're going to start doing this. And one of the things that I find fascinating, and this is part of the book, is there's this issue that if you develop a new sense and I develop a different new sense, we might not actually be able to really communicate to each other what it is like. And that's because of the fence line around our qualia, our experience. What I mean by that is if I ask you to imagine a new color, so go ahead and imagine a new color, it turns out it's impossible because you've got these firm boundaries around your experience and you say, I just can't think of a new one. But it's the same thing if I ask you to imagine a new sense, something that's not hearing or taste or touch or smell or, you feel like, I just can't even imagine something else. But no doubt when we start feeding in data from the stock market or Twitter or the drone or whatever, you will develop a new sense, not just the new capacity to detect and act on something, but a qualia, an internal experience. And the thing is, if you're doing one thing and I'm doing a different one, there's just no way for us to communicate that. For example, if you have a blind friend and you try to explain what vision is, that you capture photons from great distances and you're able to put together a picture, your blind friend eventually might even pretend that she understands what you're talking about, but she won't. She cannot understand what vision is, just like a colorblind person can't understand what purpleness is unless they've experienced it.
That's the wonderful thing about Neil Harbisson's sonochromatic sound portraits. He creates these beautiful, colorful portraits, and only Neil or only people wearing the device that he has, anyone who has an eyeball, can truly experience that artwork in the way in which he's experiencing the artwork. To everybody else who isn't quote unquote enhanced or doesn't have sensory addition, it's just this very colorful square. So we're going to end up in this moment of possible subspeciation. We're going to have a multitude of differentiated bodies, all sensing the world very differently. I mean, how do we coexist if we ever got to that stage?
Yeah, I mean, look, there's a sense in which people are all very different anyway because of their experiences and their political beliefs and so on, as we see on Twitter and Facebook and so on. And so this may be just the next step of that, where people are off in a different direction in terms of their sensorium.
So we're going to go from identity politics to morphology politics. It's going to be a whole new swathe of differentiated ways of experiencing this world. Yeah. Before we do go to YouTube questions, I want to ask you, David, about how this idea of sensory addition actually inspired an episode from HBO's Westworld.
Yeah, so I'm a scientific advisor for that show. And I said to them, like, look, we've got this great thing where you can feel any kind of data stream. And so I said, what if the military contractors who drop in season 2 to deal with these bad robots, what if they were wearing this as a way of detecting the location of the robots? And they could say, oh, there's one off to the left here because I'm feeling the vibration on my skin. And there's one behind me by 500 yards because I'm feeling the vibration on my skin. And so if anyone happened to catch this in episode 7 of season 2, that's what happens. They drop in and they can feel where the robots are and they can dispatch them accordingly. That, of course, takes place 30 years in the future, that idea. But we've used that idea in my lab for blind people. So people who are blind, they can feel the location of people around them. Like, oh, there's someone walking up from behind me and they're getting closer and closer. And there's someone over here and they're getting farther away and so on. And they can have, in a sense, vision that is better than the rest of us because we only see an angle in front of us and they can see 360 like a Jedi. And on top of that, we add in navigation directions. So if we're sending them to some particular office space or whatever, they go forward, turn left here, go forward here. And so it turns out that exact idea that we used in Westworld, we're now using in real life with participants who are blind.
We have our first question from YouTube from Leslie Ann Daly, who asks, what ethics need to be considered with things like sensory enhancement? And I actually want to take that one step further and ask, what happens when we start developing the next wave of sense-altering technologies, such as neural manipulations, nanoscale technology, and cognitive enhancers? What happens when they find our way into our hands and eventually into our heads? What sort of ethical questions will we need to start asking?
Yeah, great questions. There are a host of ethical things. And one of the important things in science is to always make sure that we're not screaming ahead of our moral compass, but instead we're dealing with these questions. And so I was actually just before we all got locked down, I was part of a terrific small conference with the top ethicists and developers of technologies to really understand and wrestle with these questions. I'll tell you just very briefly, I think something like what I'm developing with feeding data streams in, that doesn't have too much in terms of ethical problems, because in a sense, this is no different than wearing ear pods and listening to a message, or wearing, glasses and watching your screen of a phone. It's just another way of getting data in. And so the same question would apply to, hey, should we not have phone screens or not have earbuds for something? So that's not too big a deal. The bigger issues are when we start reading and writing from the brain. For example, with Elon Musk's Neuralink, which, by the way, no one has to worry about that because that's just a clinical application. What I mean is it's great technology, but that's just going to be used clinically for probably our lifetimes. And the mythology around Neuralink is, oh, everyone will get one and then you can communicate with your cell phone faster or something. No way. Because neurosurgeons aren't going to do it because there's risk of infection and death on the operating table, and it's just simply not worth it for consumers to go in and have an open head surgery so they don't have to use their thumbs. But that category of thing is the bigger ethical question. How do we make absolutely certain that, if people get that, there are no security concerns, for example? There's no way to make it's so that the company or a hacker could get in there and actually change something about what's going on with your life. As far as cognitive enhancers go, that's an interesting, tough one. I mean, we drink coffee and stuff like that, which is a cognitive enhancer. People for decades smoked cigarettes. The nicotine is a cognitive enhancer and so on. It's not clear that we're going to be able to do anything about that as those get developed. People will use them if they want to. Yeah, I think to my mind, the main one is the reading and writing to the brain. We just have to be super careful that we know exactly what we're doing with those.
I do want to ask you about Neuralink because the announcement was made on Friday, and there are a lot of promises being made by Elon Musk, and equally Brian Johnson from Braintree has a similar device, Kernel Co, which we don't know a lot about yet. But it feels like both of these individuals, what they want to do is create devices that jack into the brain. But it feels like what you're proving with Neosensory is that you don't actually have to cut the hole in the head and drill in and jack onto the brain. In actual fact, the way through to the brain is through our pre-existing sense organs. So how do you feel about these sorts of things being evangelized and advocated for?
Yeah, I'll tell you generally. So, what I'm developing in Neosensory is for feeding data streams into the brain. And so for a few $100 and with this wristband, you can get much of what we're talking about done that way, and that's great. But for anything very specific, you actually need to get into the brain. For example, if you want to help somebody with Parkinson's disease or depression that's not reacting to any other kind of medications or approaches, or epilepsy, you need to actually be able to get in the brain and deal with the brain that way. So that's where that comes in. And I think it's going to have lots of clinical application. And by the way, what Elon's doing, just for context, is people have been putting electrodes into the brain and stimulating cells and measuring from cells for 70 years now. He's just come up with a better way to do it to achieve a higher density and to make sure that you don't hit any blood vessels as you're essentially sewing these electrodes into the brain. And then also you don't have wires, it wirelessly transmits out. So he's just making, very wonderful improvements on this, and it will clinically be very useful. But that's sort of how that spectrum works. There are lots of things you can get by just feeding in new data externally, but for anything fine, like I need to change the way the circuit behaves so you don't have the symptoms of Parkinson's disease, that's where you need more detail.
We have another question from YouTube, this time from Ben Greenaway, who actually gave me the phrase plug and wait as opposed to plug and play for some of these devices. And Ben asks, you spoke of where the neuroplasticity of a child ends, and if that child lacked a quote-unquote good diet of sensory experience, it can negatively affect their adult life. But could things like sensory expansion actually cure that?
Very cool question. I don't know. I wouldn't say we have any evidence that we could do it yet, because as far as we can tell, if you have missed the critical window to learn, for example, language, it is too late. There's no way to catch up on that, even if I, stick whatever data in through the wrist. So yeah, I think it is probably too late. There are lots of doors that close pretty rapidly in the brain as the visual cortex comes into shape, as the auditory cortex comes into shape. You need the right input at that point.
There's another question from YouTube here from Lewis Johnson, who asks, is there a risk of a new breed of computer brain viruses if we start inputting new information into the brain? I mean, to me, it feels like there are so many media viruses out there that seem to get into our brains through things like Twitter or just social media. So it's really nothing new. But I guess what they mean by that question is, will people start hacking our brains directly through these new devices?
Yeah, as I mentioned, this is maybe one of the key ethical things. The questions is, how do you make absolutely sure that this is not hackable? Because now you're in the inner sanctum of the skull, and you have to make absolutely certain that nobody can start manipulating your thoughts any better than they already do with politics of social media. Yeah.
I saw an event in London, I think almost 10 years ago. The prosthetic limb user Bertolt Meyer handed over his iPhone to a gentleman called Anders Sandberg, who is a wonderful individual, but he has this very Bond villain-esque way about him. And he handed him his iPhone that was Bluetooth connected to his prosthetic device and allowed Anders to start randomly pressing buttons, which started to control the limb. And it was such a wonderful demonstration of what actually might be possible if we were able to hack at least the connection between the phones that we use and these external devices. But again, the thing that was being hacked was the Bluetooth, not the brain itself. So I guess there still is a possibility here. We have another question from Eris, who asks, are there any things that you can do to quote unquote train the brain?
Yeah, I mean, the main thing that the brain needs if you want to have good brain plasticity is novel challenges all the time. And so, most of us are getting that in various ways. But for example, when people retire, their lives tend to really shrink and they're no longer dealing with 100 challenges all the time. And it turns out you need that. There are these very great ongoing studies about taking people's brains at the time of their death and, doing analysis of their brains. And one of the things they discovered is some people have Alzheimer's disease, but nobody knew it when they were alive, because even though their brain is getting chewed up with the, Alzheimer's, they're constantly challenged and they're dealing with other people and they have chores and responsibilities and they're playing games. And so they're building new bridges in there all the time. They're constantly building these new bridges, and that means that they don't have the cognitive deficits. And so what I do, and what I think is the most important lesson from brain plasticity for everyone, is to constantly do things that are hard for you and new for you. Just what dumb examples, I often brush my teeth with my other hand or shave with my other hand. I always drive a different route home from work. And I always dive into new software and learn how to do new things. And, during the pandemic, I know that a lot of us have sort of been forced off of our path of least resistance to learn completely new things. And that is possibly the one silver lining to this whole lockdown, is that it's great for the brain, despite the stress and anxiety that everyone's feeling about this. It's great that we are off of our hamster wheels and doing something totally new and rethinking everything that we thought we knew.
I mean, we've talked a lot about the role of brain plasticity on external limbs or new senses, but what role does brain plasticity play in things like memory?
So memory is the key example of brain plasticity. Everything that you can remember, who your parents are, where you grew up, what you did last week, all of these things are because of brain plasticity, because you're actually writing them down into the structure of the circuitry. And so there are many, I actually think it's a shame that we call computer memory, because what's going on in the brain is so different than what happens in a computer. Computers write things down as little files and it's all these zeros and ones, but that's not how the brain doesn't do like a video recording or something. I can tell you a joke in English, and if you speak another language, you can turn right around to someone and tell them the same joke immediately in another language. It's because you're not storing the sequence of phonemes, you're storing sort of the gist of it, the concept of the joke. And so one of the things we've discovered over the last 50 years is all the different aspects of memory in the brain. There's short-term and there's long-term. And in long-term, there's declarative memories. In other words, things you can declare, like, this is what I did. This was a fact. This was an event. And then there's all the non-declarative memories, like how I ride a bicycle. I can't tell you how I ride a bicycle. I just know how to do it. I have remembered how to do it. Anyway, all these different types of memory are underpinned by different strategies and structures in the brain. And the brain has all these weird properties, like, I'll just mention one. Older memories are more stable than newer memories in the brain. And that's very weird. You don't find other things like that. Like in an institution or a company, you don't find that older memories are more stable. But this happens, if any of you have seen, let's say somebody at the end of their lives on their deathbed, they'll often revert to their original language and they'll be speaking their original language. They'll even have forgotten things that they learned in their teens and so on. And they'll remember their childhood. This is because there are many parameters that can change in the brain. And one of the things I argue in the book is this new framework about daisy chaining timescales together. So you have things that change rapidly. And if they present enough evidence to the next layer down, those things say, oh, okay, I guess I'll change too. And if those guys present enough ongoing evidence to the next layer, those guys say, all right, well, I guess I'll change too, and so on. And so you have this sort of working its way down into the circuitry. And by the way, this goes all the way down to the DNA in the sense of, things that happen to you a lot change your genetic expression. There's a whole field called epigenetics, which is about how these, how the whole conformation of your genome changes so that some genes are expressing more and some are getting suppressed and so on.
When we talk about memory, it raises some problematic and very interesting philosophical questions, especially about memory and this idea of consciousness. And you're a possibilian, so you've been so wonderful, especially in the last book, Incognito, at being playful with some of the multitude of possibilities for where consciousness and memory might exist, because the current consensus in neuroscience is that consciousness is an emergent property of the brain. And this feels like it's fast becoming a dogmatic, entrenched position. But that isn't the only theory of consciousness, is it? I mean, where do you stand on the idea that consciousness might actually exist independently outside of the brain and as a pre-existing condition of the universe itself, much like dark matter or dark energy or even gravity?
So that's a school of thought called panpsychism, which is that, as you said, maybe it's like a property of atoms, like spin or something. Here's what I would say. We don't know. In 2020, everyone can speculate and argue and have philosophical debates, but it's at the moment, we have to have a wide table to accept lots of hypotheses because we simply don't know the answer. And what's funny is, a lot of people will have strong opinions and get angry about one version of theories or another, but nobody knows. What is clear is that you need the physical structure to have its integrity in order to experience consciousness. And when you put even small molecules into your body, whether, alcohol or drugs or whatever, that changes your consciousness. I mean, we understand a lot. For example, take psychedelic drugs. These are molecules that bind to particular receptors on neurons, and they change the behavior of the neurons in slight ways. And that causes the whole network to behave, let's say 5% differently. And now you're seeing silver leprechauns and, having a completely different kind of experience. And so I interpret that actually, in terms of the drugs, I interpret that as an illustration of how fragile consciousness is. It needs to run just right for us to experience the kind of consciousness we're used to. And you change it just a tweak, and now you're having a very bizarre kind of thing. And so, I've totally forgotten where we were going with this. The question was...
What I really wanted to ask is, it feels like when we talk about this idea of memory, we think of the brain, we go back to those computational metaphors, and we think of the brain as storing memory. And the brain, again, as this thing like a computer in which the memory is stored within the organ, within the device. But it could be the case that the brain is not this computational storage device. It could actually be more like an antenna. It could be more like a radio or a terrestrial TV. It might actually be tuning into consciousness that's somewhere out there, memories that are out there, not actually within the brain, which is why memory is so fickle, which is why sometimes we can share memories. I know you have such a wonderful radio metaphor to describe that possible way in which we can understand consciousness.
Yeah, cool. I mean, let me say a couple of things about that, which is what is absolutely clear is that you need the integrity of the system to have normal memory consciousness. Number one. Number two is, let's separate memory from consciousness, because memory is an issue of what can I recall, whereas consciousness is the thing that flickers to life when I wake up in the morning. It's my internal subjective experience. I'll tell you, the general view of neuroscience, and I don't think this is so much dogma as just where we've sort of landed as a field, is what is absolutely clear is little bits of damage in particular spots damage you in very particular ways. You get damage in one spot, you don't have consciousness anymore. You get damage in another spot, you cannot understand music anymore. You get damage in another spot, you cannot name animals anymore. Another one, you can't see colors anymore, and so on. So we know that the physical stuff maps onto what you're able to see. What I suggested at the end of Incognito was something that I have to do this carefully, because it's not something I was suggesting is true. I was simply saying it's something that still could be true, which is that although we know the physical structure is important, it could be that the brain is like a radio. So I gave the analogy of if you were a primitive man and you found a radio in the sand and you'd never seen anything like this, and you figured out how to take off the back of the radio, and you saw all these wires, and you start realizing that if you take out this wire, it garbles the voices, and if you take out that, it stops the voices altogether. You might become a radio materialist where you say, all right, I've got it. If the wires are in this configuration, then you get voices. But what you didn't even realize is that there's this invisible electromagnetic radiation coming from a distant radio tower, and that's actually where the voices are coming from. And it would be the same situation where you need the integrity of all the circuitry to function fine. but it's not actually the origin of it. So I suggested this radio hypothesis just as a way of sort of completing the picture of what is possible on this wide table of what we should be thinking about. As far as panpsychism goes, by the way, I think it's fair with all these theories to say we just don't know. The weird part about consciousness is not only do we have a theory to explain it, but we don't even know what such a theory would look like. We don't even know, because of the difficulty of what we're trying to explain, as in, I can say, okay, I've got all these tools in mathematics and science where I can say, okay, carry the 2 and do a triple integral over here and so on. But at what point do I say, okay, that equals the smell of cinnamon or the taste of feta cheese or the beauty of a sunset or the redness of red or the pain of a stubbed toe? It's like, this is one domain over here and experience is this other domain. It's not even clear how to bridge those.
Might it actually be a case that we will never bridge it because of the limitations of knowledge in the human brain? I'm reminded of your story in some 40 Tales from the Afterlives, where you wake up on the slab surrounded by the aliens prodding you, going, "What is answer? What is answer?" But you're too evolved to explain it to them. So I just wonder if we will just never get there purely because we'll never be able to look at ourselves objectively, because we will always have this subjective thing called a brain, which is filtering the information that we receive about the world.
Yeah, it's a good possibility. It's impossible to know because every generation feels like, okay, here's what we know, and it's impossible to think about the next step. But then 100 years later, you look back. I mean, just think about what our neuroscience textbooks will look like in 2120 when people look at the shit that we have now, and they'll say, God, how do these guys not know that? For example, the main textbook in our field is called Principles of Neuroscience, and it's that thick. It's like 800 pages. That's not principles. If it were principles, it would be the size of a pamphlet. All we've done is we've just dumped every piece of data in there. We don't know the principles yet. And that's actually one of my big goals in writing Livewired, is to figure out what are the key things that we should be paying attention to here.
Yeah, it does feel to me like Elon Musk is a radio materialist, that he's going to go with Neuralink poking around the brain in the hope that he's going to eventually find memories so then he can upload those into whatever uploaded consciousness that him and other transhumanists potentially want. And I do wonder whether what he should actually be doing is developing a Wilhelm Reich-esque morphogenic field detector, and that might actually have a way to discover where consciousness is. Maybe, I tell you what, Peter Thiel should take up that. He should be the heretic who goes after the idea of trying to tune into collective consciousness, and Elon can go after the idea of memory and consciousness existing in the brain, and we can have a Freud versus Reich style fight on our hands.
I think that's a great idea. I think that's a great idea because I want to say that the idea of materialism is probably right. Like, that's where I'd put my chips, given that we don't know. And, maybe in 100 years, we'll think very differently about this. But I think it's probably a good idea to rule that out first, if you like, to go after that. And only if you fail, only if you say, wow, we've measured everything in the brain now at high resolution, every spike in the brain, and we're still stuck, then it's worth going to the next thing. But you have to solve that first thing first in order to rule out materialism.
Well, that's the joy of being a self-styled possibilian. And perhaps you could quickly explain that to our audience who don't know. But when I first came across that idea as an undergraduate, I thought it was such a wonderful way with which to look at the world, to be open to a multitude of possibilities. We have good knowledge about certain ones, but that doesn't mean that we won't have alternative knowledge later on down the road. Why do you think it's so important to stay open to a multitude of new ideas, to be a possibilian?
Yeah, I mean, the thing that always strikes me as strange, and by the way, you see this with everyone's political opinions on Twitter and Facebook and so on. But, what started this whole thing for me is, I would go to the bookstore and you'd see the books by the religious fundamentalists and you'd see the books by the neo-atheists, and they were, polarizing each other and arguing. But the fact is, there's so many more possibilities than there's a guy with a beard sitting on the cloud, or there's nothing at all of interest in the cosmos besides that. And there's this whole space of possibilities. We don't know what the heck's going on. And so that's why I coined this term possibilianism, which is the goal is to understand the structure of the possibility space so that we can drive our science forward and rule out parts of the possibility space and open up folds that we didn't even realize were there in other parts of the possibility space. And so my whole view on this is, and I think this is just an expression of the scientific mentality, is just if you know something for sure, then great. But most things we don't actually know for sure. And so there's no point in fighting and dying and pretending that I absolutely know the answer to this when you just don't. And in fact, if you look at the history of science, in every generation, people feel like, okay, look, we've got all the facts. And so this should be the thing. But, you can't even imagine understanding whatever, the northern lights before you understand the magnetosphere of the earth, or how muscles work before you have the concept of electricity, or, any of the, like, you just didn't have the facts there. And so you can argue to blue in the face, but you just need to find the next step. And that's what possibilityism is about.
It's always going to be this process. We have another couple of questions from YouTube. As always, a fantastic question from Tracy Follows, who asks, you talked about enhancements to individual brains, but how will these sensory expansions or data streams connect with each other in a collective consciousness or hive mind? How will these ideas help us to connect with each other better?
Very cool question. One of the things we've now built in my lab is you can use a smartwatch to pick up on things like, heart rate and heart rate variability and galvanic skin response and other things like that. And what we've done is use the API in the watch to hook into, to feed that data to the wristband. But it's not your own wristband, it's someone else's. So imagine, Tracy, that you and let's say you have a husband, feel each other's physiology. So you are across the nation and you are feeling your husband's heartbeat and everything. And you think, oh man, he's feeling really stressed out. I better call him and check and see what's going on with him. So this is an experiment we're just beginning to now, by the way, married couples might not they might think this is the worst thing in the world, but who knows? The key is, what is it like to be tapped into someone else's body physiology, even just an expression of it? And so this is our first foray into having a different kind of thing where you're not just experiencing your own body, but you're experiencing other people's bodies. And from there, we can expand that. So I love your question, Tracy, and check back in a year and see where we've gotten with this.
We've got another question here from YouTube, really about health, and it's from Anne McQueen, who asks, insulin regulation and blood sugar impact on long-term brain health. Is there any benefit to a ketogenic diet, a low-carb approach to maximize long-term brain health and or dementia prevention? Really, it's a question about, is there anything we can do in terms of our diet or in terms of our health that will improve our possibility for things like neuroplasticity?
That's a great question, and people have been studying this. It turns out, I didn't realize this until a few years ago, but these studies in nutrition and what you eat and so on are extraordinarily hard to pull off well, because people lie on these things. So when nutritionists are running these studies, they run 1,000 people and they say, oh yeah, I didn't eat any high carb things, but in fact, they just scarfed the chocolate cake in the fridge and they just don't want to admit it. So it's difficult to know, and it's certainly difficult to know how that plays out 50 years later in terms of dementia. So I don't know, but the reason I smiled when I first started hearing the question is because one of the things we're doing, by the way, is hooking the sensory buzz to a continuous glucose monitor for people with diabetes, so that they can just have an awareness of where their blood sugar is without having to check their phone and look at the graph through time and so on. You just have a sense of, oh, okay, it's going down. It's no problem yet, but it's on the way down. Oh, now it's getting really worrisome. Now I'd better find food. You're getting all these signals to tell you that continuously in a way that you don't have to pay attention to, but you are aware of that at all times. And I think this is going to be really useful as an immediate step to help people with about their blood glucose.
We've got another question from YouTube, this time about AI, which is from Onar, who asks, is it possible to generate a really creative AI without a plasticity-like structure of the brain? And I guess to add on to that question, do you think we're actually going to learn from brain plasticity and how we create future machines, future AI, future robots? Because right now, AI seems very fixed. It doesn't have that plasticity. It doesn't have that ability to self-configure or to live wire. So do you think all of these things will eventually inform the way in which we design machines or even architecture in the future?
So this is exactly my hope, is that this book will launch a whole new era of the way we think about designing machines. But I will say that the way machine learning and AI work currently is a form of plasticity, which is to say you've got this giant network with lots of units and connections, and depending on the data coming in, it's changing the strength of these connections around. So it is exactly something that took inspiration from the brain, but then went off in its very simplified direction. Now, what's happening in AI is extraordinary. It's amazing stuff that's going on there, but it is sort of like a simplified cartoon of the brain. And you can get really good things. What you can't get right now is artificial generalized intelligence, where it's good at many things and it doesn't fail catastrophically if you change the game on it a little bit. But I just want to clarify that it is using the very basic things that we figured out about plasticity some decades ago, which is that neurons change the strength of their connection. Now, one of the arguments I make in the book is the connection strength between neurons is only a tiny bit of what's going on. What you have are changes in not only the synaptic strength, but the receptor distribution, the biochemical cascades inside the cells. And as I mentioned, all the way down to the nucleus with the expression of genes. So you've got lots of plastic parameters, and current machine learning only uses a tiny sliver of that, but we're learning a lot from it. And I think AI and neuroscience are in an interesting dance, learning from one another as we go along.
We've got a great question from Sarah Tico, who asks about representation in the field of neuroscience. She asks, what are the ethical implications of entrepreneurs and researchers developing novel models of sensory communication when they tend to represent a demographic unrepresentative of the population as a whole? So I guess really it's a question about diversity of people within the, not just neurodiversity, but diversity of thought and diversity of individuals within the neuroscience field.
Yeah, I mean, look, everybody's interested in getting more diversity and a diversity of ideas as a result of that. And that's something, as you may know, Silicon Valley is an extremely liberal place. And so everybody's trying their hardest to make sure that they have their funnel for applications for employment as wide as possible so that that can be achieved. That said, I think that science can be actually independent of that. So when Newton discovers F equals ma, or D equals 1/2 at squared, it doesn't matter that he's a white male. It's just a true piece of the universe that anybody can then use. And so what is lovely about science is it doesn't actually have to traffic in this issue of the politics of, oh, but was that a black man that discovered that, or was that a white? It doesn't matter. It's a true piece of the universe that has been discovered. And so our job is, as members of society, is to make sure we've got a wide funnel and try to get everyone participating in this. The good news is that I think the most important step that's ever been taken in this direction is just the advent of the internet. It means that knowledge is available to everybody. Any kid, any boy or girl, any ethnicity, anywhere in the world can access all of the world's knowledge and springboard from there.
So for anyone who's listening to this podcast or watching it online now, and they hear about this idea of live wiring and they want to explore it personally themselves, how can they go about leveraging the neuroplasticity of our brain today? And what do you think they might be able to do in the near future to explore previously invisible aspects of reality?
So I'd say a couple things. One is that what we have done with the Neosensory Buzz, I think I mentioned this before, but we have an open API and we have SDKs for Android and iOS and other computer languages. And what we encourage people to do is try feeding in any kind of data stream that they're interested in. And so we actually just ran a developer contest that's still in the middle now, but we have 8 semifinalists who are all doing extraordinarily cool projects where they're feeding data in to Buzz. So if anyone's interested in this, you go to neosensory.com and you scroll all the way to the bottom where it says for developers, and you click on that and you can find out exactly how to do that. And all the SDKs are free, of course. And so that's a way that people can do it. The second thing, of course, is buying the book and reading about the experiments in there. And the third thing, I'll just mention, there's a new company here in Silicon Valley called Luminary Cafe. It's luminary.cafe. And they just launched last week, and I am proud to be the first luminary on the site because they're just getting rolling, and they did this so it would be in time for my book. So what I've done is filmed a series of lectures with videos and color and incredible ways of experiencing the stuff that goes beyond the pages of the book. So if anyone's interested, go to luminary.cafe and you can, actually watch the videos and take a deeper dive that way.
So I guess there you have it. It's time to use the body and the brain as a platform for a multitude of possibilities of sensoriums and of experiences. So David Eagleman, I just want to say this has been an absolute pleasure. Thank you for joining us today.
Great to see you again, Luke.
Thank you to David for sharing his unique perspective on how humanity might use neuroplasticity to its advantage. You can find out more by purchasing his new book, Livewired, The Inside Story of the Ever-Changing Brain, available now. And don't forget, you can watch the full unedited video of this conversation at futurespodcast.net, where you can also find out about all of our upcoming live stream events. If you like what you've heard, then you can subscribe for our latest episode. Or follow us on Twitter, Facebook, or Instagram at Futures Podcast. More episodes, transcripts, and show notes can be found at futurespodcast.net. Thank you for listening to the Futures Podcast.